All right, so this is a review of everything we've covered since the first exam. Okay, so since then we've been learning all about continuous populations. So we've got a random variable like age, IQ, weight, time that we are sampling from. And so we've learned about the continuous uniform, normal, student's t, and chi-square distributions. Now, some of our applications have been from some other kind of population, like we're going to roll the die or flip a coin and see what happens. And so that would be basically the kind of content we covered in exam 1. So for each of these new distributions, the uniform, normal, t, and chi-squared, you need to know how to find their mean, standard deviation, and of course, if you can find standard deviation, you can find variance. You need to know how to find the probabilities. So you need to know how to use your normal CDF, TCDF, chi-squared CDF, find the area of a rectangle. Okay? You also need to be able to find percentiles. Right? The 10th percentile or 95th percentile of a distribution. Right? Like how old do you need to be in the oldest 10% of all people in a room? That's a 10th that would be a 90th percentile. In addition to learning how to find the probabilities and percentiles of these new distributions, right? All along this semester, we've been looking at what happens when we take samples from a population. Specifically, we've looked at the set of all possible sample means that we might get when we take samples of a certain size, right? And so there's this kind of sub or hidden population made up of the sample means, okay? And that population has a distribution and a mean and a standard deviation, like pretty much every other population or distribution we'd ever run across. Okay, so we've also looked at sample proportions, p hat, and how they behave as a variable. And again, they have a distribution, a mean, and a standard deviation. Right? And the third variable we've looked at is our sample variance, s squared, or related our sample standard deviation, s. So x bar, p hat, and s, these sample statistics, when we say we're going to randomly collect a sample from the population and calculate the sample mean, that's like saying, I'm going to reach in behind the scenes to all of the possible sample means and pick one of those out at random. So these three variables are a large part of what we've been concentrating on since the first exam. X bar, p hat, and the sample variance s squared. So now let's look at each one of these individually. So we're going to start with x bar. Okay, so what do we know about the mean, variance, and standard deviation of x bar? Okay, we do know that the mean of the sample means is going to be the mean of the population from which we've collected our data. Right? And the standard deviation of the sample means will be equal to the standard deviation of the population we're collecting our sample from divided by the square root of the sample size. Okay, so we have those two facts to work with. Okay, those are always true no matter what. Now, the one thing we got to be careful about is the actual distribution of the x bars. Okay, so your sample mean, x bar, is normally distributed only when the population that's being sampled from is normally distributed. Okay, now, we have a second case, okay, which says that x bar will be approximately normally distributed, even though the population is not normally distributed itself. Okay, but as long as our sample size is large enough, our sample means will start to exhibit the behavior of a normal curve. Okay? And the final fact we have related to the distribution of x bar is that x bar, not only is it not normally distributed, okay, when the population is not normal, but if the sample size is too small, we can't even use an approximation of a normal curve for x bar. Right? So when my variable is the sample mean, like earlier I said, what's probably the average height of 100 random people is more than 6 feet tall. Okay. First thing I want to establish is, do we know the distribution of x bar? Okay, and we're going to walk through these. Is the population normal? If not, do we at least have a large enough sample to make up for it? Okay, otherwise, there's nothing we can do about it. So, in general, right, we're going to look at a problem like this. Okay, so what's the probability that the sample mean is between two numbers? Okay, and I'm just going to use number 1 and number 2 here, for example. Number 1 could be negative infinity if you just want to be smaller than some number. Negative 2 could be positive infinity if you just want to be bigger than a number. Or those could be two finite numbers, like from negative 4 to positive 83. Okay? But when I'm looking at trying to find the probability of the sample mean is smaller, larger, or between two numbers, I have to walk through my conditions. Okay, and the only way we have to solve this problem is if, one, the population we are sampling from is normal, therefore x bar will be normal, or two, the population of x bar is going to be approximately normal, even though the population we're sampling from is not, as long as we have a large enough sample size. Okay, and again, 30 is our cutoff. Remember, there's nothing really magic about 30. But as long as we meet one of these two conditions, then x bar can be approximated with the normal curve, which means we're going to use our normal CDF. We're going to go from our lower limit of number 1, upper limit of number 2, plug in our mean and standard deviation of x bar into the normal CDF function, and boom, we have our answer. That will tell us the probability that the sample mean for a certain size sample is between whatever the two specified values are. Now, we could also, instead of adjusting the mu of x bar and sigma of x bar inside the normal CDF function, we could take the numbers 1 and 2 and convert them to z-scores using this conversion formula. So for x bar down here in the bottom left-hand corner, the formula, we would plug in number 1 and out would be a z-score. Okay, plug in number 2, out would come a different z-score. And then we do the normal CDF between those two transformed z-scores. And of course, the mean and standard deviation for z are 0 and 1. So anytime it's an x bar probability problem, I have to check my conditions. Are we allowed to say x bar is, or at least is approximately normal? If we can, then we know normal CDF is how we're going to find probabilities. And then we either adjust the mean and standard deviation of x bar, or we convert the x bars to z-scores. Either way is 100% fine. So now, let's look at an example problem. Okay, so take a second to read through this. Okay, we're going to assume that the T-Hill route takes, on average, 24.4 minutes to circle campus and come back to where it started, with the standard deviation of 3.9 minutes. Okay, so that's the population we are sampling from. Okay, we know mu is 24.4, we know sigma is 3.9. So we want to find the probability that the average amount of time it will take for 18 random round trips to be more than 27 minutes. Okay, so it's a probability problem, and specifically it's probably that the average amount of 18 random trips. So that is a sample. So that is screaming average of a sample, x bar. So we want to know the probability that x bar is greater than 27, or if you will, between 27 and infinity. Okay. Well, to do this, because the individual round trips of the hill route, all right, are normally distributed in terms of how much time they take, all right, then x bar will be normally distributed. So we're going to do a graph of a normal curve. All right, x bar is my variable. We know the mean of the x bars is 24.4 because that's the mean of the individual random round trips. Okay, the probability that x bar is greater than 27 will be equivalent to the area to the right of the 27. And so now I just need to find that blue shaded area. And we're going to do that by doing normal CDF to infinity. We need to put in the appropriate mean and standard deviation for x bar. And so the mean of the sample means is 24.4 because that was the mean of the original population, the individual bus trips. And the standard deviation of x bar, the sample means, is the original standard deviation of 3.9 divided by the square root of the sample size, which is 18. So we put it all in our normal CDF, and out comes roughly 0.0023, and that's our probability that if we take 18 round trips, the average amount of time would be more than 27 minutes. So remember when we said we wanted to find the probability that x bar does something, there were two ways to handle it. We could, like we just did, right, adjust mu and sigma inside the normal CDF, okay? Or we could use this conversion formula and turn our limits on x bar into z-scores. Okay, so in this case, we want x bar to be more than 27. So we plug in 27 for x bar. Okay, and we get the corresponding z-score of 2.828. Okay, so 27 minutes for an average of 18 bus runs is the equivalent of a z-score of 2.828. Okay? It's just like converting from feet to kilometers, Celsius to Fahrenheit. We're just changing scale. So, we want the probability that a random z-score is bigger than 2.828, because that would mean x bar is bigger than 27. We're going to do our normal CDF from 2.828 to infinity with the mean of 0 and a standard deviation of 1. And we get 0.0023 just like we got before. Okay, so now we're going to turn our attention to the sample proportion, p hat. Okay, so here we're interested in doing an experiment like flipping a coin, and we need to know the probability of actually getting heads, or we're going to roll a die and talk about the probability of getting a 3. Okay, if it's a fair 6-sided die, that probability would be 1/6. Okay, so when we want to know what are the chances that the sample proportion does something, first we got to know the real probability of that event happening in the population we are collecting our sample from. Okay, so if the coin is fair, the probability P of heads is 1/2. If we're rolling a fair die, the probability of getting a 3 is 1/6, and so on. And we need to know that because that's going to tell us the mean of our sample proportions and the standard deviation of our sample proportions. Okay, so both of those are going to be based on the real proportion or probability of the event we happen to be interested in. Okay, now, the distribution of p hat, okay, so p hat is just my variable. Okay, it's going to be approximately normal as long as we meet this sample size condition. Notice this is not the same as n being bigger than 30 that we needed for x bar a minute ago. It's a different scenario. We need n times p hat and n times 1 minus p hat to be bigger than 5. Okay? Or if we haven't collected the sample yet, so we don't know what p hat is, then we need n times p and n times 1 minus p to be bigger than 5. Okay? Now, what these are really saying simply is that whatever we're interested in, getting heads, we need at least 5 heads and 5 tails. If we're rolling the die and we're interested in getting a 3, we need at least 5 threes and at least 5 rolls that aren't 3. Or at least we need to expect that based on the sample size and the actual probability of the event happening. Okay? So, under these conditions, right, we can find the probability that p hat is bigger, smaller, or between two numbers. Okay? So, let's look at this in general. Again, p hat's my variable. If we've decided that we met the conditions where p hat is approximately normally distributed, we're just going to do normal CDF between our two limits, put in the appropriate mean and standard deviation for p hat, crank out our normal CDF, and we've got our answer. All right, so let's look at a specific example here. Okay, and again, you can also convert p hat to a z-score if you prefer to do the conversions on these, same way we could with x bar. Okay, so let's look at this example. So we're still talking about the hill route and how much time it takes to complete a full loop. And we know the mean is 24.4 minutes and the standard deviation is 3.9. And now the question is, what is the probability that less than 10% of 140 round trips will take more than 30 minutes? So 10% of the 140 round trips, those 140 round trips are a sample, right? 10% equates to a proportion of 0.10. Okay, so this is asking you the probability that p hat is less than 0.10. Right? So we have to check our conditions. Right? If we meet the right conditions, p hat will be approximately normally distributed, and we're good to go. So let's take a look at those conditions again. We need n times p hat to be bigger than 5. Now, we haven't collected our sample of 140 trips, so we don't know what p hat really is. We're actually interested in what are the chances of p hat doing something. So here we'll look at n times p, because we don't know p hat. And remember, p hat is the probability of the event actually happening. And the event we're interested in here is a round trip taking more than 30 minutes. So, to find the actual probability that a round trip takes more than 30 minutes, right? Well, the round trips themselves are normally distributed, so we're going to go normal CDF from 30 to infinity. The mean and standard deviation of a round trip are 24.4 and 3.9. So we get about 0.0755. That is the actual probability that a random trip, okay, will take more than 30 minutes. All right, now that's P, N we know is 140. So if I take N times P, that's 140 times 0.0755, I get 10.57, which is definitely larger than 5. Okay, and 140 times 1 minus that probability of 0.0755 gives me 129.43. Okay, so we are expecting about 10 or 11 trips out of our 140 to take more than 30 minutes and about 129 of the trips to take less than 30 minutes. So we've met our at least 5 that do and at least 5 that don't meet our criterion. Okay, so P hat will be approximately normally distributed in this situation. Okay, so we want the probability that less than 10% of our sample of 140 round trips, all right, takes more than 30 minutes. So P hat is my variable. We've established that P hat is approximately normally distributed. So over here on the left, we need to know mu of P hat and sigma P hat, which means we need to know the real probability, which we established just a second ago. The probability that one random round trip takes more than 30 minutes is 0.0755. Okay. So we want the probability that P hat is less than 0.10. The mean of the P hats is the actual probability, 0.0755. Okay, so we need to do our normal CDF, all right, from negative infinity up to 0.10. We need to plug in the appropriate mean and standard deviation for P hat. Okay, and again, the mean of P hat is P. The standard deviation of P hat is that big giant square root of P times 1 minus P over N. So everywhere we see a P, we're going to plug in 0.0755. Everywhere we see the N, right, inside the denominator of the square root, we're going to plug in the sample size of 140. And out comes our probability of 0.8637. Okay, so again, that means if we take 140 round trips on the hill route, right, the probability that less than 10% of those trips will take more than a half hour is 0.8637. Now, because P hat is approximately normally distributed, we had the option of adjusting the mean and standard deviation to fit for P hat inside the normal CDF, right? Or we could have converted P hat to a z-score using our conversion formula over here. So I plug in 0.10 for P hat, plug in 0.0755 or all the P's, okay, and we get the corresponding z-score of 1.097. Again, just changing units from the original P hat, 0.10, to the corresponding z-score of 1.097. So the probability we're after would be the probability that the z-score is less than 1.097, which we would get with the normal CDF. Okay, plugging in the z-scores, negative infinity and 1.097, and the mean and standard deviation for z are 0 and 1. And we get pretty much exactly the same answer we got the first time around. Okay, and again, either method is perfectly acceptable. All right, if you don't like doing these transformations, just adjust mu and sigma inside the normal CDF. If you don't really like adjusting mu and sigma inside the normal CDF for X bar and P hat, convert X bar and P hat to z-scores. Either way is perfectly fine. All right, so the last thing we want to look at is our sample variance, or S, our sample standard deviation, either way, okay, as a random variable. Okay, so as a variable, we don't know the distribution of S squared. Okay, it's not a nice, easy distribution. However, under the right circumstances, we can do a transformation that'll take S or S squared and turn them into chi-square scores. And we do know how to find probability with the chi-square distribution. Now, that condition is simply that the population you are sampling from must be normally distributed. If it is, then we can use the formula n minus 1 times S squared divided by sigma squared, and that'll turn S or S squared into a corresponding chi-squared score. Okay, now, let's look at an example. Okay, so again, I'm still dealing with the hill round trip times, and I want the probability that the standard deviation, Okay, and the amount of time it takes for 27 random round trips. So again, those 27 round trips are a sample. So we're talking about the standard deviation of a sample. That's what we want to know. What are the chances that S, the sample standard deviation, is between 4 and 6 minutes? Okay. Now, we know that the individual bus round trip times are normally distributed. Therefore, we can turn S into a chi-squared score using this transformation. We just have two different values for S to transform. So I'm going to start by plugging in S equals 4. Okay, our sample size is 27. Okay, we know sigma is 3.9. Plug all those in. And so a sample standard deviation of 4 equates to a chi-squared score of 27.35. Similarly, we want to turn the upper limit for S, which is 6 minutes, into a chi-squared score. So we're going to plug 6 into the equation. And so we're going to have 27 minus 1, sample size minus 1, times S squared divided by sigma squared. That is 61.5385. And so the probability that S is between 4 and 6 becomes the probability that your corresponding chi-squared scores show up between 27.3504 and 61.5385. Okay, and we find that using our chi-squared CDF. Again, lower limit, upper limit, degrees of freedom. Now, I want to pay attention. If we look at our transformation formula, right, it says that n minus 1 times S squared over sigma squared gets you a chi-squared distribution with n minus 1 degrees of freedom. N is my sample size, 27. So n minus 1 would be 26. That's how I know, and that's the only way I know, I have a chi-squared with 26 degrees of freedom. Okay? Also, we want to remind you that on a chi-squared distribution, the mean is always equal to the degrees of freedom. Okay, so that's now how I know to put the 26 in the middle. And a chi-squared graph always starts at 0, so there's nothing to the left of the 0 over there. Okay. I want to look at this problem, exact same problem, but had it been phrased slightly different. So what if it is said instead, what is the probability that the variance in the amount of time it takes for 27 round trips is between 16 and 36 minutes squared? Okay, so instead of S being between 4 and 36, I'm saying S squared is between 4 squared, which is 16, and 36 squared, which is 36. Okay, so really it's the exact same problem, only instead of saying standard deviation in the problem, it says variance. Okay, now, that does mean we have to change slightly what we do, or at least that's one way to look at it, right? We're still going to use the same conversion formula, but the limits on S squared are 16. So 16 is going to get plugged in for S squared. Notice I'm not squaring the 16 again because that is the value of S squared already. And 36 is my upper limit for S squared, so I'm just going to plug that in. Okay, so 16 and 36 go in where S squared goes. Before, 4 and 6 were going in where S went, so they still had to be squared. And we get the exact same chi-squared scores because it is the same question, which means, of course, we're going to get the same graph and the same probability. Okay, so whether these questions about the variance and standard deviation are asked in terms of variance or standard deviation, all that means is whether or not you have to square S inside the formula. And if you have S to plug in, you got to square it to get S squared. If you already have S squared, you don't have to square S squared to get S squared. That's all we got to do on that. All right, good luck. If you have any questions about the topics covered in this video, or anything else that's happening in your statistical reasoning class, talk to your instructor, go to their office hours, or take advantage of the free tutoring available in the Math Tutorial Center. Good luck, and go Vols!